Why does a motionless skater tend to remain motionless? The short answer to that question is that an object at rest tends to remain at rest. In other words, if you leave a motionless skater completely alone, you don't push on her, she'll remain motionless. This behavior is known as inertia, and objects in our universe exhibit inertia. But don't take my word for it. Let's do some experiments so you can observe it for yourself. For our first experiment, I'm going to perform the classic parlor trick of pulling the tablecloth out from underneath the place settings. It's actually not a trick at all. It's physics in action. These are objects at rest, and it is their nature to remain at rest, as long as we don't bother them very much. Minimal external influences. And because I'm using a very slippery silk tablecloth, and because I'm going to pull it very fast, I will influence these slightly, but it'll happen so quickly and for such a short period of time that they'll pretty much be unaffected, and they should stay put. Now, the whole idea of this being called a trick brings up an issue with this class. This class is not about magic, it's about unmagic. Whereas magicians try to hide from you what is actually happening, they keep their secrets. I'm trying to give away all the secrets. It's unmagic. You should understand everything that happens and why it happens. If in doing a demonstration, this one in particular, but others as we go through the world of how things work, if I fail to convey to you why it happened, what you're seeing and why it happened, then I have missed my goal. So, these are objects at rest. It is their nature to remain at rest. They exhibit inertia. And so as long as I don't bother them, they'll stay there. So, add a degree of difficulty. And I have found over the years that I have to be nervous about this, because if I get complacent and do it casually, then I flip everything over. So, I'm nervous about it. Here we go. I'm going to give myself some room to get my hands moving nice and fast before the tablecloth pulls tight. I'm definitely not going to pull up. I'm going to pull a little down so that I don't fly everything around the room. Ready? 3, 2, 1. There we go. Objects at rest, remaining pretty much at rest. You can try this experiment yourself, but you might want to start with unbreakable dishes. If you don't want to risk anything, you can also do the experiment with a handful of coins and a sheet of paper. Just lay the coins on the paper and snap the paper out from underneath them. The coins will stay in place, objects at rest tending to remain at rest, because they exhibit inertia too. This demonstration of inertia, that an object at rest tends to remain at rest, makes use of a pencil, a wooden hoop, and a glass bottle. All right, here we go. First, I put the hoop on the bottle. Next, I try to balance the pencil on the hoop. And that is not easy. I did it. And now I'm going to sneak the hoop out from underneath that pencil. I'm going to grab the hoop very fast so that the pencil is suddenly left hanging in midair. It will remain in place because of inertia alone. It's an object at rest, and it will tend to stay at rest, even as the hoop disappears from under it, and it then begins to fall. Ready? Get set. Ta-da! Let's take a look at that one again in slow motion. Watch how the pencil just hangs there in midair for a few frames before dropping into the bottle. This brings us to the question I asked you to think about in the introductory video, about whether a rotary lawnmower can cut the grasses with its fast-moving blade if those grasses aren't attached to the ground. Inertia makes it possible for the lawnmower to cut the grasses even when they're not attached to the ground. Each grass remains in place not because it's held there by anything, but because it's an object at rest, and it tends to remain at rest, even as a sharp blade cuts through it. Rather than cutting grasses, though, I can show you the same effect by cutting an apple with a sharp knife. This experiment is designed to answer the question, can I slice through an apple even if that apple isn't being held in place by anything? In this particular case, I'm going to place the apple on the table, and then I'm going to slice it horizontally with a knife, or at least try to. Now, I'm not much of a swordsman, so if I try to swing that knife through the apple by hand, sometimes I hit it and sometimes I miss. So, I have built a spring-loaded apple slicer. This baby has a strong spring. Look at that serious spring. And I've got the knife on a swivel so I can make it swing around here nicely. And I can adjust the height. So I'll adjust it right there for the middle of this apple. It's all good. And the spring is so strong I have to hold the table in place. I am going to get the spring all lined up here with the apple. Notice the apple is not attached to the table, just sitting there minding its own business, but it's kept in place by its own inertia. And we'll see whether this knife can get through the apple. Okay, now I stretch the spring and get ready to let go. Here it goes. Ready? Get set. Sliced apple. Now, we did exert a little bit of external influence on the apple. The apple did finally not completely stay put, but it stayed put enough to make nice, even slices right through that apple. So, the question is answered. Yes, it is quite possible to slice an apple that is not held in place by anything, but that is simply an object at rest, tending to remain at rest. Just as a fast-moving knife can slice through a stationary apple, so the fast-moving blade of a rotary lawnmower can slice through stationary grasses. The blade sweeps so quickly through those grasses that they don't have to be held in place. Inertia ensures that they don't move as that sharp blade cuts through them. Many kitchen tools take advantage of inertia. They use a fast-moving blade to slice through objects at rest. A food processor dices onions, a blender crushes ice, and a spinning blade coffee grinder turns coffee beans into ground coffee. So back to skating. Because of inertia, a stationary skater tends to remain stationary. That's the nature of things in our universe. And while it's not very exciting to stand motionless on your skates, it's a relief to know that you won't suddenly start moving swiftly in some random direction for no apparent reason.